Worry. Right. So we start our discussion. This is the lesson number 4. So the module scope for today is binary addition, including the generation of CNV flags. So these are the flags that we want to focus on. More specifically, these are ALU related stuff. So you might have to understand these things very well. For the most time, there's a question raising related to this one. So strongly encouraged to go through very well. Arithmetic and logical operations, addition, subtraction, multiplication, and division. Now, as we already know, LU is not much focus on this division work. Instead of rest of the things are the main focuses. And operation, O operation, XO operation, shifting, rotated, and stuff. So these are the major things that we want to understand how it works. Then finally, we are going to discuss status flags, status or the flag registers as like CNV flags. Interpretation of flags in, sorry, there's double ins in here, in computation. So how these flags are working and stuff, these are the major things that we want to focus on today. So if I'm not mistaken, the first question is focused on this scope. Last couple of, not last forever. This is the first question, and it was a bit complex question. It's not hard, but it's quite easy. But you need to apply it. That's the only consideration. So the agenda for this discussion is binary addition, a small revision that we want to do. Revision on ALU, we'll do it later on. Adder circuits, more specifically half adder and full adder. Flag registers, flags in ALU, arithmetic instruction and flags, logical instructions, measurements of computer power. This is one of important point, more specifically like you can think some of additional resources regarding this one. Then finally, we'll do a group activity. Now, students for the group activity. So for the housekeeping, yeah, mark your attendance. Very first question. Mark your attendance. Quickly add your marks. I want to send them. You know, you are getting emails from Udan, right? If you are not attending to the classes, not really. This class, none of students was caught at, but today they'll caught it. So that's the thing. You can add your attendance. Then ready for the activity. Next one, creating groups. How can I create groups? Now students, right nowadays. Revision question, not done. I plan to do it nowadays at all. Done, not really good. Once you completed, you can mail to me nowadays at all. And today we have to do a lot of work using pen and paper because computer might get much of time because we are mainly focusing on ones and zeros. It might be much easier if you are using a pen and paper for today work. We start with the standard discussion, binary addition. I quickly solve this question, guys. One plus one plus one plus. Don't get lazy. Even a single student is in there, no worries at all. This is something usual in online classes. If sometimes they join and run here and there, sometimes they don't join. No worries at all. Yeah, continue. Quickly go to the printing place and tell, I don't. Can I have a A4 paper? Digital, I guess. Do you have any other assessment submission today? Due today? No. Then probably they all went for a movie or something. You don't have that kind of unity, right? This batch, I don't see that kind of a unity. You have this that kind of a unity. No, have like people are going to movies and stuff. Going. Ah, That it's simple, right? So 0, 1, it's 1, 1, 1, it's 2, 2 we can't allocate, so we have to go to 0 and we have to carry 1 to this place. 1 plus 0 plus 0, it's a 1. 1 plus 1 again it's a 0 and carry it 1. 1 plus 1, 0, carry it to the next, and 0, 1, it's a 1. 1, 1, 0, again it's a 1. 1, 1 is goes to here, 1, 1, 1 comes to here, 1 goes to here, 1, 1 comes to here, and 1, 0, 1 comes to here. Okay. Simple question. So all you need to do is you need to understand this carry, how this carry is working. Yeah, and ALU, probably you know what is ALU. It's just for mainly focusing on mathematical and logical structure. It takes two inputs and process the data and gives the output. Once it comes to this ALU, so you need to understand how this ALU works or how these instructions are getting. For that, we have two main things. One is adder circuits, the other one the adder circuits. Once it comes to adders, we have two major adders. First one is half adder, the other one is full adder. Do you have anything to full adder and half adder? No. Right. Now these are adder circuits. Now we'll get an example. Now we want to take one uh, 1 plus 12. We'll assume 1 plus 12. The final answer is 30. Now, a human brain can understand this 13 easily because we want to do a small mathematical calculation. But once it comes to a computer, we want to convert this 1 into a digital and 12 into again, it's a digital value. 8, 4, and sorry, 8, 4, right? 8, 4, 0, 0. So this is 12. So what computer does, computer converts this 12 into binary, then it converts this 1 into binary. Then 1, 1, 0, 0, then 1 comes to here, then there is a plus sign, then it comes to 1, 0, 1, 1. Then only we can create this 13 and it converts into a value that a human interpret to decimal value, which one much easy. The question is, if something we want to carry, as an example, you just think about now in this case, if we have 1 here again, instead of 12, if it is 13 plus 1, if it is 13 plus 1, 1, 1 is goes to a 0, and we want to carry an additional 1. We want to store this 1 in somewhere because computer would not able to understand unless. Clear? So the calculation is 1 plus 1, 0 comes to here. We can let it to know, but we want to keep one carry bit outside. To keep this carry bits, we want an additional layer. For this part, if you have only these two, then half adder is more than enough. We can go for a half adder circuit. If we want a carry layer or an additional layer to store the data additionally, then we want to go for a full adder. That's the only thing you need to understand. Right, we'll do a small question, then you might get much experience on this. Now we'll start with a small activity. You just draw the truth tables for AND and XOR operations for two inputs. We'll get an example A and B, two inputs A and B. Just draw truth tables, AND operation and XOR operation. Hmm? You just think the first one, there are two inputs A and B. You just go for to the n minus 1. Then there are two, so we have to go for 4. Two zeros, one ones. Then 0, 1, 0, 1. Then go for end output and the XOR output. End operation. Perform end operation for A and B and XOR A XOR B. What are the outputs? Done. Done. Right. So basically, what happens in end operation? It it's like multiplication. Zero multiplied by zero, it's a zero. Zero multiplied by one, it's a zero. One multiplied by zero, it's a zero. One multiplied by one, so it's finally one. So this is the output for AND operation. If we take XOR operation, then zero zero becomes a zero. Zero one becomes a one. One zero becomes a one, and one one becomes to zero. Correct? Correct. So if we take this AND and XOR operations, we can uh, imply or we can give an additional value or some, and we can get some understanding how these mathematical activities are working. As an example, you just think we can take this AND and XOR operations in our full adder and half adder. Still it might be confused. We'll go to the next step, then you might be understand what is happening there. We'll take the first one, the half adder. Half adder is the basic digital circuitry that performs addition to single bit binary numbers. You should understand it's two single bit binary numbers. As an example, A and B. So these are the inputs, A and B. So A and B are the inputs. So 0, 1, 1, 1, 1, 0, or another thing. This is the basic additional operation. So two inputs that we have. Then it produces two outputs, a bit and a carry bit. Now, once it comes to this adders, we have a carry bit. We have a carry bit. Then we are focusing on how these summations are working. A half adder works by examining the two input bits A and B and producing a sum and a carry bit. So I'll show the diagram, then you can understand a bit more. Now, as an example, we have A and we have B and we have AND operation, and we haven't thought about a carry operation, an additional carry. As an example, if it is 1, 1, 1 plus 1, it's 2. So we don't have a position to add this 2. Instead of what we have done, we have focused on AND operation, O operation, XOR, not. So those gates we have used. We haven't added two values using truth tables up to now. Addition is wasn't happen. Multiplication and stuff, some other logics was happened, but we haven't added. So this adder means we are adding together. We are calculating. It's 1 plus 1, 2. This kind of thing is happened in this half adder and full adder, both of circuitries. While half adder is useful, the adding two single bit numbers, it cannot handle carries from the previous addition. As I told you, we can do we can do easily for these calculations. A, B. If we have addition C, D, yes, of course we can. Half adder can do all of these things, but the unfortunate situation is if there's a carry bit someone out from something else, then we can't do. As an example, think output comes from a one circuitry, then it needs to push into the input for another circuitry. We are unable to take this input. That's why we are going for a full adder. So you will get to understand a bit more these things. So basically half adder is basically happening all of this addition. For example, if you are in two 4-bit numbers, two 4-bit numbers, you would need to use a full adder circuitry which can handle carries from previous addition rather than a half adder. If we have only two values, then no worries at all, we can manage using half adder without any problem. But if expanded a bit more, we want an additional layer for this handling of a carry bit. Still, it might be confused, but I will show you the truth table of this half adder. Now you can see it's a bit different than you have learned up to now. Up to now you have done like if there's equal or if it is 1 and 0, then you are doing something to one single column. You haven't gone for a carry forever, isn't it? And operation or not XO whatever, it has if there's two inputs, then not only a single output in there, only one single output. Now we have two outputs. For an adder circuit, we have two outputs. One output is the sum, the other output is the carry bit. How to calculate or how to draw this truth table? You just add 0 plus 0. Then sum is 0. If sum is 0, do we want to take something to out? No need, we don't want to. So we have to give the carry as it is. 0 plus 1, sum is 1. Do we have to take something out? No. So we have to keep the carry as it is. 1 plus 0, again the sum is 1. And do we have to take any other thing to out? No. 1 plus 1, yes, sum is 2. So 2 is not allocated. 2 means 0, 1. Then 0 stays in the sum and there's a 1 carry which we are taking out from the calculation. Got it? This is how, if there are two inputs, the ALU performs the work. Got it? How ALU works, if there's two inputs, then there's a specific sum column and there's a specific carry column, then it calculates and gives the value. That's all. This is a very simple thing, right? This is a very simple thing and it works like this. And next, what we have to do is we have to understand full adder, how this full adder works and how this full adder is going to work. A full adder is more advanced digital circuit that performs addition to two single bit binary numbers as well as a carry that results from adding two previous bits. Now we have an additional layer which takes two inputs and we are calculating. We'll get an example, then you can understand. It produces two outputs, some bit and a carry bit as usual. Then a full adder works examine three input bits. Now, two input bits, last time we have understood, all right? If there's only a situation 1, 1, then we are going for another carry. But if there's 3, the possibility of getting carriers is higher than higher because one, if there are two ones in any column, so we have another carry. If there are three ones, then definitely there's a carry with an addition. Got it? That's the difference in between this full adder and a half adder. The sum bit represents the result of adding the three input bits together, while the carry bit represents any carry that occurs when adding the three input bits. That's the story. The difference of this full adder and half adder, we can take some input stream as an external component. Then we can do whatever the calculations. That's why we want to understand, all right, we have another additional carry from somewhere else. This is the place that flags are being required. An additional layer to store all of these things. Right? We'll do a small activity. This is a small truth table for full adder. Now just add. You just do the same thing for what we have done for half adder, but in this case we have an additional layer which is carry. Right? We have another carry additional bit. This is the standard inputs A and B, and additionally we have additional carry bit. Right? Do the sum and carry out quickly. Just add the values. That's it. Yeah, just add these three all. That's it. Yes, sir. Why you late? Huh? Huh? I? Okay. You came to this campus. Because I have CCTV access. I can see who came at what time. So I know everyone who comes to this place at what time came, what time left. If you want, I can give the time. That's right. Just check. No, it's for my. No, no. You can have all the records in that post page, or else I'll share my previous recordings, which we done for the online classes. I'll share those recordings. Then you can go through if you want, because it was like same thing, same syllabus, same thing. We haven't changed anything. We haven't changed. Extract. You got it. You not really, you didn't get it. These videos, not. I will share. Done. 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 Ambani. Done. No, 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 no. I didn't do the whole thing. What? I didn't know. I don't try to lie. No, no, I didn't like. Yeah, I did. Doing that, just add one calculations. Right? If you do, lazy, lazy presence. What? Zero, 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 zero. Zero. Sum is zero. Any? Zero. Zero, zero. No, one. This at least is zero plus zero plus one. So it's one. Right? Like if you carefully see what is the output, you can see there is an AND operation and an XOR operation. Can you check whether your output is